If we want to talk about logic circuits, first we need to talk about minterms. Important points about minterms include the following. In a minterm, each variable x, y, or z appears once, either as the variable itself or as the inverse. Each minterm corresponds to exactly one entry or row in the truth table. Implications of the 2 points above are that you can build any Boolean function at all by building it from minterms. Truly, any Boolean function can be constructed using minterms, and the construction process is simple. First, get a truth table for the function. Be sure that all possible combinations of variables and inverses are accounted for. For each entry of the truth table for which the function takes a value of 1, determine that corresponding minterm expression, remembering that every variable of its inverse will appear in every minterm, or all the minterms from the second step together. To illustrate the use of minterms to get an electrical implementation of a logic circuit, consider this problem. Three young graduates have formed a company: Alicia, Ben, and Corey. They have a system to minimize problems. For all minor decisions, they want to use a circuit that will determine when a majority of the three of them has voted for a proposal. Essentially, they want a box with three inputs that will produce a 1 at the output whenever two or more of the inputs are 1. This is the truth table for that problem. After getting the truth table, the next step is to identify the minterms. The minterms are to the right of the corresponding entries in the truth table. There are 4 1 entries in the truth table and 4 corresponding minterms expression. So when you AND all these terms together, you get 1 under the conditions here. These are the 4 conditions that get a 1 in the truth table. And this is the result, or the f, that will be the function that represents the truth table. Each minterm can be generated using a 3-input AND gate, and the first minterm is shown below. You will need 3 more circuits somewhat like this one for the complete solution. Next, consider how these small circuits must interact. The function is 1 whenever the first term is 1, or when the second term is 1, or when the third term is 1, or where the fourth term is 1. To implement that, you'll need the following circuit. Now let's talk about max terms. A max term is a logical expression of n variables consisting only of the disjunction and logical complement operator or denial. Max terms are the dual expression of minterms. Instead of using operators, we use and, or operations proceed similarly. This is an example of a max term and how you can write it as the example on the right. Like minterms, maxterms also provide a way to represent any Boolean function algebraically once its truth table is specified. For example, for the same function as previously, we observe that it is 0 on rows 0, 3, 5, and 6, so the function will be equal to that. And this is how you can write the minterm or the max term for that function. Then we will talk about the Karnaugh maps. A Karnaugh map, or K-map, is a pictorial method used to minimize Boolean expressions without having to use Boolean algebra, theorems, and equation manipulations. A K-map can be thought of as a special version of a truth table. Unlike a truth table, in which the input values typically follow a binary sequence, the Karnaugh map's input values must be ordered such that the values for the adjacent columns vary by only a single bit, for example 00, 01, 11, and 10. This ordering is known as a gray code, and it is the key factor with regard to the way in which Karnaugh maps work. The Y column in the truth table shows all the zeros and 1 values associated with the gate's output. Similar maps can be constructed for 3-input and 4-input functions. In the case of a 4-input map, the values associated with the C and D inputs must also be ordered as a gray code, as we can see in this picture. Consider an example: 3-input function represented as a black box with an associated truth table. And here we have the truth table and the graphical representation. Any pair of horizontally or vertically adjacent blocks corresponds to minterms that differ by only a single variable. Such pairs of minterms can be grouped together and the variable that differs can be discarded, leaving a much simplified equation. As we can see in this picture, it shows the process. Then grouping can also be formed from 4 adjacent minterms, in which case 2 redundant variables can be discarded. Here are the equations for each grouping. As you can see here in the picture, you get the final function based on the minterms.
Okay, let's talk about the Boolean algebra. What is the Boolean algebra? Well, it was created in 1854 by George Boole, and it was named after him. It's been said that the Boolean algebra is a lot alike of the ordinary algebra. And it's also been said that the people that are good at the ordinary algebra are going to be good at manipulating the Boolean algebra. The best part is that the Boolean algebra only has addition and multiplication, and it also has only 2 numbers, the 1 and the 0. But they are alike just a little. Let's see why. In the multiplication, they are a lot alike. But when we do some additions, we can see that they seem a lot alike, but then there's something wrong. Let's see again. In the ordinary algebra, 1 plus 1 is not equal to 1. So let's say something. Let's imagine that you have something and nothing. Something is going to be 1 and nothing is going to be 0. So now we can do this easier. If you have something and then you added nothing, you end up having something. And then if you have something and then you add something else, you end up having something. So 1 plus 1 is equal to 1. So if you're paying attention, they look like logic gates. But what happens when we add some variables? Well, they can only be zeros and ones because they are Boolean. And as the ordinary algebra, they might be represented by any letter. So let's see some examples. Let's say that we want to add a plus 1 or multiply a times 0. So let's say that a is equal to 1. A that is 1 plus 0 is going to be 1. A that is 1 plus 1 is going to be 1. So we can say that it doesn't matter what is the value of a. If it's added to 0, the result depends of the a. But if it's added to 1, it doesn't really matter what is the value of a. But then it changes when we multiply the a. So here we can say that it doesn't matter the value of a when we multiply it by a 0. It will be always a 0. But it really matters when it multiplies by a 1. The value is going to be the value of a. So now you know a little bit more about the Boolean algebra and the variables.
Hello, I'm gonna talk about the basic functional blocks. First, we have the decoders. A decoder is a combinational logic circuit that converts binary information from input lines to a maximum of 2n unique outputs called the n to m line decoders. For example, we have the 2 to 4 line decoder and the 3 to 8 line decoder. This is a circuit from a decoder. This is a 3 to 8 decoder. As you can see here, we have 3 inputs that decode 8 outputs. The 3 inverters provide the complements of the inputs, and each one of the 8 AND gates, these ones, generates one of the mini terms. This is an easiest way to explain it. If you receive simple information, for example, the inputs X, Y, and Z, you're gonna get a 1 in a D0 and so on. You only get one of these signals per input code. Then we have the encoders. This performs the inverse operation of a decoder, has 2n or fewer input lines and n output lines. The output generates the binary code corresponding to the input value. This is an encoder. As you can see, it's the opposite from a decoder. You have here 7 inputs and it's going to turn it to 3 outputs. This is the Boolean output function. Even D1, D2, D3, D5, D7 is going to be given by C. J can be, Y can be D2, D3, D6, D7, and so on. But there is a table to explain it even better. As you can see here, the relationships, again, is the opposite from the decoder. You have X0, Y0, C0. So you're going to have a 1 in D0. You have 0, 0, 1 because you have a 1 in the D1. You have 0, 0, 1, you're going to have a 1 in the D1. If you have 0, 1, 0, you're going to have a 1 and so on. Again, it's the same. You're just going to place one of those signals here and it's going to give you this. It has its limitations too. The first is that only one of the inputs is allowed to be 1. When all inputs are zeros, the output is 0, but this situation is the same as input D0 is equal to 0, to 1. Then we have the multiplexers. This is an example of multiplexers. As you can see, you have 1, 2, 3, 4, 5, 6, 7. You have 7 throws to 1 output. This is the easiest way to explain it. If in S you have a 0, then the upper gate, this is an AND gate, is enabled and E0 has a path to the output. So goes through here, it activates this gate, and it goes all the way here. If S is equal to 1, then you're gonna let the path to the AND gate to the I1. A multiplexer or data selector is a combinational circuit that selects binary information from one of the many input lines and directs the information to a single output line. This is a 4 to 1 line multiplex. This is a functional table. And this is the logic diagram of that functional table. It applies like the same logic. So you can see we have S1 and SO, well, S0. S1, if S1 and S0 is gonna be equal to I0. So if this is 0 and this one is 0, you're gonna open this gate. If S1 is equals to 0, we go all the way through here, but the S0 is gonna be equal to 1, you're gonna open H1 for J. If S1 is equal to 1, we have S1 here, it goes all the way through here, but SO is equal to 0, you're gonna open this gate, I2 for the J. If S1 is equal to 1 and SO is equal to 1, 2, then you're gonna open I3. For last, we have the demultiplexers. Performs the inverse operation. A multiplexer is a circuit that has one output and more than one output. It is used when a circuit wishes to send a signal to one of the many devices. The selection of the specific output is controlled by the bit combination of n selection lines. Again, it's the same. You have the data input here. So, for example, it says if S0 is equal to 1, you stop here, and S1 is equal to 0, then you're going to open the D1. If SO is equal to 0 and S1 is equal to 0, then you're going to open D0 and so on. You need to follow the logic, and for that you can use a truth table. Okay, this will be all for my part. If there is any question, doubts, or correction, we will listen to them and try to do our best with suggestions. Thank you so much for your attention and have a good day.